So in this section, we're going to move beyond integrals of just one variable. So we've seen how to do regular integrals with one variable in Calc 1 and Calc 2. And in this class, we've looked at line integrals where we're integrating over a curve. Now we're going to start integrating over regions in R2. So we're going to start for this section. We'll begin with rectangles. So we're going to integrate functions of two variables, but we're going to integrate them over regions in the plane. So let's go ahead and see how we do this. So let's suppose we have a pile of snow. So the first slide had a pile of snow, so that's our motivation here. We're going to suppose we have a pile of snow and that at each point xy below the pile of snow, our function h of xy gives the height of the snow. And what we want to do is we want to estimate the volume of snow in this pile. So let's recall from Calc 1 how we did this when we were first starting out with integration. So we approximated the area under a curve, and we used a bunch of rectangles to do this. And the reason we did this is because we knew how to calculate the area of a rectangle. And the more we saw, the more rectangles we used, the better the approximation to the area under the curve. So we want to do the same thing now. We want to use a familiar shape in 3 dimensions that we can calculate the volume of. So for this, we're going to use boxes now. So what we're going to do is we want to calculate the amount of snow in this pile, and we're just going to go ahead and say, let's let x be between -2 and 2, and y between -2 and 2. So we'll just start off with supposing our snow pile, we just want the volume over this square in the xy plane. And one way we can look at this is let's consider the level curves of our function for a moment. So let's suppose this is a picture of our level curves for our snow pile. And we can see it's kind of just shaped like an upside down parabola here. And so all of our level curves are circles. And of course, the heights here at the 1.8 is telling us this is about, say, 1.8 feet or meters, depending on how big our snow pile is. So how are we going to use this? Well, remember when we were doing functions of one variable in Calc 1, we broke up an interval into subintervals to work with. So we're going to do the same thing here, but we're going to break our rectangle up into 4 subregions like this. Or our square in this case, we break our square up into smaller squares. So we started off by a 4 by 4 square. Now we have 4 of 2 by 2 squares. So our next step when we were doing this in Calc 1 was to pick a point in each subinterval. We do the same thing here, and we're going to pick points in each of the subregions. So we can see here we have in this subregion we pick this point here, in this subregion we pick this point, and this point, and this point. And we're picking them, in this case I'm picking them right on the level curves, so it'll be easy to tell what the height of the function is at each of those points. So we'll denote these points we picked 4 of them. So let's say P1 is x1, y1, P2 is x2, y2, P3 is x3, y3, P4 is x4, y4. And so now over each of those points, we form a box of the height of our function at that point. So that box is going to look something like this. So in each of those 4 regions, we have a box above the region, and the height of that box is h of xi, yi. So similar to how we formed the rectangles in Calc 1, we just have one more dimension, so we're forming boxes here. And so now the volume of our snow is approximated by the sums of the volumes of those boxes. And we can see here, so V is our volume, so it's approximately the height of the first box, which is h of x1, y1. And then the area of the base of that box is delta x, delta y. And similarly, we add on the volume for the second box, third box, and fourth box, and this gives us our approximation for our volume. And so if we look back at our contour plot, we'd have the point x1, y1, the height there is about 0.4. At x2, y2, the height was about 1.5, and so on. We also saw that our delta x and our delta y, those were the sizes, the width and the height of each of our sub-squares in our region. Each of those was 2. So if we fill all of those in, we get our volume as about 16.4. So very similar to how we did Riemann sums in Calc 1. It's just now we have that extra dimension to work with. So the question is, okay, this gave us a volume. Can we do better than this? Well, in Calc 1, when we wanted a better approximation, we used more rectangles. So same approach here, we'll divide our square up into even more. So each of those subsquares, will divide that into 4 squares. And so now we have 16 total squares subdividing our region. And again, we just pick a point in each region. So notice each of the subsquares here has a single red dot in it. And those are our sample points. And then we just form boxes of those heights just like before. So here instead of 4 boxes, we have 16 boxes to approximate our volume with. And so now we sum 16 boxes with these 16 different heights, and then our delta x, delta y now has gotten smaller because we divided it further, so those are 1. And you could go through and pick off what each of those heights was from the contour plot for each of the points, but we're not going to do that here. It's a little tedious to go through and do this for 16 points and add them all up. Hopefully it's clear what the method is, and you could go ahead and do that by hand if you wanted to. Now, this will give us a better approximation than our volume approximation with just 4 boxes if we use 16. But we know from Calc 1 to get better and better approximations, we used more and more rectangles. So similarly, to get better and better approximations to the volume, we're going to use more and more boxes here. So here's a picture if we use lots and lots of boxes. And we can see now this is looking more and more like our pile of snow. So it's looking more and more like this paraboloid that's giving us our region of snow here. And so this is similar to when you used more and more rectangles in Calc 1. It became closer and closer to the area under the curve. So we can now go ahead and define what we mean by the definite integral. You should be able to guess what it's going to be. Let's just start with a general function now and not worry about snow anymore. So we have some function f of xy, and our region here is still going to be a rectangle, but it doesn't necessarily have to be a square at this point. Just any rectangle will be fine. We're going to divide this up so we know that if I want m subintervals in the x direction, I take delta x to be b minus a over m, and we want n of them in the y direction. We don't need to have the same numbers. So we'll take that to be d minus c over n. And then we just define the xi's. We start when I is equal to 0, we're just to a, and then x1 is going to be a plus delta x, x2 will be a plus 2 delta x, and so on. And similarly for the y's. So this is exactly how you divided up an interval in Calc 1. Now we're just dividing it into rectangles instead. Now for each of these little rectangles, we're going to choose some point inside the rectangle. So just like we did above with the snow pile. And then we can form this Riemann sum, and this Riemann sum is exactly what's approximating the volume like we saw in the snow pile. And you should be able to guess at this point, well, to get a definite integral, if we want to get the exact volume, or just the definite integral in this case, we want to take more and more rectangles. So we want to let the interval from a to b be divided up into more and more pieces, and the interval from c to d be divided up into more and more pieces, which is the same as letting the limit as m goes to infinity and the limit as n goes to infinity. So this is our definite integral. So one thing to notice here is we have this, when we were writing definite integrals in Calc 1, it was always from like a to b over some interval. In this case, we just write it with a subscript r for now to say it's over a rectangle. You will find some textbooks use 2 integral signs with a subscript r. For us, we're just going to use one integral sign with a subscript r when we're just saying it's over some region r. We'll see when we go to actually calculate these and we put limits on them, then we will use 2 integrals. But you should be able to tell from the context of the problem that in this case, we're doing it, since r is a region in the plane, we're doing an integral with 2 variables. You can also see the 2 variables in the function. You can also see the dA is saying some little incremental area size. So delta x, delta y gives you a little area. And so that's what our dA stands for. And so this is our definite integral. And as you can imagine, we don't want to actually calculate integrals using this formula, just like we didn't want to calculate integrals using this formula in Calc 1 and Calc 2. So we're going to see how to actually be able to evaluate these integrals in the next section. For now, we're just going to be doing approximations of this integral using some reasonable to handle Riemann sum here with a reasonable number of m and n. So this is how we set up a definite integral over a region R when that region happens to be a rectangle. Of course, we don't want to limit ourselves to rectangles to work with. It's a little different than in Calc 1, where really an interval was the region to work with. And you could have multiple intervals and stuff, but for the most part, you wanted to work with intervals. In this case, we can have all kinds of interesting regions. Like our region, for example, could be a circle with the inside of it shaded in, and that's a perfectly interesting region, and that wouldn't fall into the region of being a rectangle. So what we can do for this is the regions we're going to be working with, for the most part, we can enclose that region in a rectangle. And then we can divide that rectangle up into a bunch of subrectangles like above, and then we can consider only the rectangles that lie inside the region when we form the Riemann sum. So we'll throw some of those rectangles away if they don't completely lie inside the region. And then if we take the limit and let those rectangles keep getting smaller and smaller, eventually they'll fill out the entire region, even if the region is not a rectangle. So it'll work out just fine even in that case as well. And that's the basic idea for definite integrals of functions of two variables. So we should be able to understand what they are at this point in terms of a Riemann sum, and we'll work in the future about how to actually calculate these integrals.